device for more appropriate utilization. Now, excuse me, the obvious answer is, well, then you just test for everything. You test the memory, you test the CPU, you test the radios, you test all the sensors somehow, you test the graphics, you test the display, the audio, on and on you go, and you test all these things. Well, yeah, okay, that would be a solution, but it's not very practical, because by the time you finish the testing, the phone's going to be out of production and you're going to have to start all over again. So you can't do that. So what do we do instead? Test. We think the answer is to establish a suite of tests, and that's maybe a little bit easier said than done. Hopefully, by the time this day's over, we'll be able to figure out if it can be done or not. Excuse me. We think that if you pick a few appropriate tests, and those tests are fair and objective, then maybe we could come up with a mutually agreed upon suite where all of us, you guys talking to the consumers, us talking to the OEMs, all of us could come up and say, look, here's the suite of tests we're going to use, and this is how we're going to evaluate the various devices that we get to evaluate, the ones that we have access to. So we've looked at a few. Oh, wait, I'm getting ahead of myself. Okay, so I said this already, didn't I? So that was Google Glasses, I guess you saw that. I think that the ultimate goal will be to build a test that tests for augmented reality. Now that's going to be difficult, and we're not going to do that today. We're probably not going to do that this year. When you think about it, augmented reality, and I assume you all know how it works and what it does, my feeling is that the test for augmented reality, we're going to have a jig of some type where you put the device in it, but it's going to have to be held stable so they can look at something consistently and then give you a measurement of what it sees. So it's going to take some doing to come up with a test that would be that good. But I think it should be and could be a goal. I don't know how it's going to come about right now. It's just an idea that we have. The folks that I've spoken to in the industry about it all agree that this would be a great thing to do. None of them have an idea of how to do it. They've all had ideas about how to do various pieces of it, but not how to do all of it. And so, talking about augmented reality, I just wanted to make a little joke here. So, I used to make a joke about people who take their phone. We have a person in this room that does this, by the way. I won't mention Jarvis's name. And they hold their phone, you see, down like this. They do this. Yeah, I'm paying attention to you. Oh, yeah. I call that the BlackBerry roll, because that's where I first saw was people doing it with their Blackberries. So now what we're going to have is augmented reality glasses, and you're going to think everybody's staring into space, looking up here at this lens instead of looking at you. So that's what augmented reality is going to bring us if we go with Google Glasses. So our goal is to get started. We can't wait for it to go. We've got to get going. The market's growing, the market's moving, new technologies are coming in all the time. Consumers are genuinely confused. I don't know how many consumers you guys speak to, probably far more than I do. But the few that I speak to always say to me, well, how do I know what to buy? What's the right thing? And I don't have an answer for them. I tell them, buy what you can afford. Buy the most of what you can afford. If you think you can spend $100, spend $105. You won't be disappointed. But beyond that, I can't tell them because there's no good answer. I mean, I could, interview them and say, well, how are you going to use your phone? And the answer there is, oh, no, send text, email. No, they don't know. So how are they going to be able to evaluate it? So until we get a mobile device, until we get an AR test suite, oops, where the hell did I go? Hang on, just a, someone take a slide out of here? And oh, this is interesting. So someone took one of my slides out. Okay, sorry. There are a few suites that we found, and Scotty is one of them. And I'm sorry that this came out, But we found a few of them that we thought would be useful, and I'm going to suggest that you guys use those. I don't know what to do about this. Well, Tim, can you help me?
You're talking about kind of the system level?
Yeah, we had three tests that JPR, we came up with 3 tests, and we asked Qualcomm, what do you think of these? And they said, actually we had 5, and we presented 5, and Qualcomm came back and said, well, we think one of these isn't so good, but these others are pretty good. And I had the damn list, and I'm sorry I don't have it memorized, but hopefully today you'll get exposed to them. So that pretty much is my story. Take note of my email address if you don't already have it. I have to run and catch an airplane, so if I can't answer all your questions right now, don't be shy about it, or if you don't want to ask them publicly, don't be shy about sending me an email. I answer all of my email. And so with that, I'll ask you, do you have any questions?
Hi, Sasha Segan from PC Mag. I 100% agree with 90% of what you said, especially about trying to create user experience-based benchmarks. But I'm a little perplexed about your pivot to talking about augmented reality, because now you're talking about an application that nobody today uses, that many people, that is very divisive among analysts, that many people think is a BS show-off function that not a lot of people will ever use. So why not try to focus on a scenario that includes more of the common functions that people generally agree on rather than this kind of pie-in-the-sky possible future use that is still highly controversial?
Yeah, that's good. Hold that. And I hope everybody heard him. He has a good outside voice. That's a very good point, and it shows very clearly the differentiation between you guys and us. Is that the kind of testing that we do is designed to stress machines that aren't built yet. We're trying to help the OEMs hit goals that are not currently in the market. So to Sasha's point, it would be more appropriate to test on machines that are running applications that are available today. And so you're right on the mark there. So if you disagree with me 10%, that's fine. You're correct. With regard to augmented reality, this is I don't know how to say it, maybe a personal opinion. I personally think augmented reality will be the killer app. And the reason for it is because it's going to bring so much to our lives and empower us to do so many things that we just can't do right now, but we'll be able to do much more easily and in commonplace. But again, Sasha's correct. We're not going to see it this year, and we may not even see it next year, but it is definitely coming. All of the vectors are pointing in that direction, that that's where we're going to go, and that the mobile device is definitely going to be an augmented reality machine. But and that's one of the reasons we can't test for it yet, is because we really don't know how this elephant is going to shape up. Anything else? Any other questions? Come on, you guys, don't be shy. Okay, be shy. I'll go to an airplane. All right, so you got my email. Any other questions? Shoot them at me. Just one other thing I want to tell you is, those of you who know me know that I'm not a commercial kind of guy, and I had a little bit of trepidation about coming here and doing this, and what turned me around is these Qualcomm guys. From what I've seen of the stuff that they're going to present and the way they're going to present, you're not going to hear any commercials today. So you can be comfortable. This is going to be a really good engineering day. I think you're going to enjoy yourselves.
So thank you very much, John. Really appreciate the time. When we looked at the rest of the agenda, we wanted to kind of cover the big three, certainly. So CPU, GPU, and web browsing. So we've got a series of presentations, and we've also got a representative from RightWare here to kind of go through in depth each one of those areas. The next step up is Travis Lanier. He's the Director of Product Management in our CPU group, and would be happy to present to you to show you a little bit more under the hood of the CPU.
Okay, so I'm going to be talking about CPUs and how it fits into the mobile phone system. But before I actually start talking about the CPUs, I am going to mention one thing in general about Qualcomm. So we have the Snapdragon chips. And one thing I really want to point out is that a lot of the times when we're out there, we're talking about the high-end type of devices. So when it comes out, they're excited about the latest and greatest high-end phone. But I want to point out that we create whole new generations of chips each time. So we have S4, but that's not just these things at the top. We actually come out with new chips all the way down to the bottom. So we continually invest in new technologies from the highest-end devices down to these ultra-low value devices. And we're actually expanding to televisions. So we cover a lot of screens with these technologies. So, as most of you probably know, when we create our Snapdragon processors, the CPU portion is based on the ARM ISA. And what that means is we license the ISA from ARM. All of the Qualcomm CPUs that are shipping right now are based on the ARM v7A ISA. So that means that they're compatible with all the Cortex-A processors. So Scorpion and Cray use the same instruction set you'll see in other ARM CPUs. So this means there's no fragmentation in the space. Code that runs on one CPU or another ARM CPU runs on a Qualcomm CPU and vice versa. So there's compatibility and no fragmentation throughout the ARM ecosystem. So what do we do differently? So we design our own CPU. Why do we do that and what's different? Well, the thing that we license from ARM is this top half up here. That's called architecture. And then what we do differently is what's called microarchitecture. So the things that are architecture are kind of what's visible to the programmer or to applications or the operating system. And that's what determines your compatibility. So once you have this, then you have a common set of tools, common instruction set. Everything works together nicely. The microarchitecture is kind of one that is underneath that. And that's what determines the performance of your system. So how fast does the code run? What's your power profile when you run that? So that's the number of execution units you have, how deep your pipeline is, the design of your cache system, the interconnect. For the most part, these are kind of invisible to programmers, but what you do notice is the final experience of how quickly it runs. So that's the difference between Qualcomm CPUs and the CPUs that other people are using. Now, a lot of you here got started in the PC space. So you're looking at phones now, and a lot of you continue to look at the PCs. And when you're comparing one CPU to another, it was relatively easy back when it was just single CPUs. A new generation of CPUs came out, you ran some benchmarks, it was better, right? Then the next thing came out, and there was multiprocessing. And generally what you would have is different numbers of cores. So the more cores, basically the same kind of core architecture. Generally people wanted more cores. Whether there were more applications out there that took advantage of it or not, yeah, more cores is a good thing. But kind of the unique situation we're having right now in the mobile phone space is we have different CPUs coming out. So what happens when you have 4 cores, but then you have another set that's a dual core, but it's a different core inside of it. So the point is that these individual cores that make up your multiprocessing system are not necessarily equal. And you can probably find benchmarks or applications that would look better on either one of these. So the question is what application do you care about? So I know a lot of people, when we came out with the 8960 earlier this year, they went out and they benchmarked against some of the quad-core systems that were out there. And a lot of people were like, oh, okay, it's a dual-core. I wanted a quad-core system. But they went and ran the benchmarks, and they were kind of surprised in a lot of cases. It benchmarked higher, or the same or higher in many cases, as a quad-core system. And the reason is that if you look at it, it's not just the number of cores you have, but what's the IPC of your CPU. In this case, you can see we actually came out with a quad issue CPU, whereas a lot of the quad-core systems out there, while they were superscalar awesome, they could only issue 2 instructions per cycle. So both these are different techniques for accelerating your applications, and they both have merits. Multiprocessing was out there, but I will say multiprocessing requires rewriting of your applications, and there's actually many applications that don't benefit as much from multiprocessing. Whereas when you come out with a wider instruction issue, or you go more superscalar, basically you get immediate benefit to all your existing applications, and most applications will benefit from that. So what I want to point out when we're coming out with 8064, it's not just quad-core, it's quad-core of the next generation CPU architecture. So the next thing you might wonder about is, okay, we have a quad issue CPU, the more IPC you get, generally the more power you're going to burn. So how did we deal with that? So the first thing I'll say is that when we design our CPUs, we get to focus pretty much on mobile. So we know these things are going into phones, and we make certain trade-offs to try to get the performance within a certain power profile. So for the first things, obviously we don't look at servers. If we're going to mobile phones, we don't have to do server applications or benchmarks, so we don't focus on that. Then there's other types of workloads. I don't want to say workstation, because as tablets are getting more towards content creation, that's kind of some workstation type apps. But definitely compute type applications, not something you're actually going to focus on in a CPU in the mobile space. Because you've got a lot of other resources out there, like your DSP or your GPU. So why are you going to focus on compute applications on your mobile CPU? So if you focus on these areas, what you can do is wind up over-provisioning your CPU. And you wind up, some of the benchmarks very well, may not necessarily be suitable for the mobile space. So when we look at our what we're going to design our CPUs for, obviously we're looking at mobile, and the top things that we're worried about is web experience, gaming, and user interface. And of course, all this has to be considered in the context of power and thermal. So each one of these has certain things that you can focus on. Web experience, obviously how fast your browser runs, JavaScript. And then actually something that's often overlooked is how well is your CPU integrated with your network stack. So we tend to integrate remotely with our devices a lot of the time. That might have a pretty serious impact on performance depending on how you optimize your software stack. For a gaming perspective, don't ignore that. So for a gaming perspective, we tend to focus on floating point and neon. So floating point is very important in games. We'll talk a bit more about that in a minute. And then another thing we have is a focus on neon integers. So that helps a lot of your multimedia performance. And you'll find out that neon is often used in the UI in Android. Does everyone know what neon is? No. Okay. So you're familiar with MMX or AVX on Intel processors? So this is our SIMD instruction set in ARM SA. We tend to call it Venom or Venom at Qualcomm. But all ARM processors, all ARM v7 processors have neon on them. So it's SIMD has SIMD integer and SIMD floating point. We'll get to that in a minute. So we talked about what we do. We have a quad issue CPU. So what do? We focus on the applications that we're concerned about. Some applications will run better than others, but we tended to focus on ones that were mobile. The other thing that we do is we actually have custom circuits. So this allows us to achieve higher frequency than most competing CPUs in the mobile space. Well, higher performance, higher frequency within a strict power budget. Just to give you an explanation on that, a lot of times when you go out and license a core from ARM, what they do is they run it through the standard tool, and what you get is what you get. We actually still have a lot of guys in a room somewhere with beards and lamps sitting up drawing individual circuits to get the optimum performance from the design. So that costs a bit more, but you do get extra performance for your power budget. And going to what John was pointing out here earlier, here we have a heavy focus on floating point and SIMD. All the ARM processors have that, but I'll point out we focus on having 128 data bit path compared to everyone else. Most other implementations you'll see out there will have a 64-bit data path for their neon. So again, this helps a lot with your multimedia and with your gaming. The last thing I'll point out is we also have ASMP technology. I'll talk a bit more about that in a minute, but basically what it allows you to do is run your CPUs at different frequencies and voltages. So it helps you save power in the multiprocessing system. So I talked about how floating point was very important to gaming, and Tim's going to be up later and he's going to tell you a lot more about it. But lately people have gotten very focused on just the GPUs, but I want to point out that CPU performance kind of goes hand in hand with that. If you don't have enough CPU power to pre-process everything before, or you can hand it off to the GPU, your system performance will lag also. So they kind of go hand in hand. The GPU is the big heavy lifter for most gaming applications. But here we have a slide just talking about some of the things going on in a game that are actually all on the CPU side. So the artificial intelligence of your enemies out there, if these ropes are swinging wind, it's the physics operation. all these particle effects, projectiles, collision detection, and all the animations of these guys. These are all running on the CPUs. And so games are going to probably be one of the things that really starts to push multiprocessing in the mobile space. So just to show you how this multiprocessing can take advantage of gaming, we outlined some of these things on the previous slide. So your AI, your animation, some of the pre-rendering. And here you can see a quad-core configuration. And we put each one of these individual functions onto its own CPU. So this is a coarse version of that. If you go to the next slide, ultimately the next step would be to take each one of these operations and then multi-thread those. In this case, you have fine-grained multi-threading. So you're splitting out each one of these operations amongst all your CPUs. So earlier I mentioned ASMP, so we call this asynchronous symmetric multiprocessing. What this allows you to do is it can scale the load to the appropriate amount. So I mentioned how we have a separate voltage and a separate clock for each one of these CPUs. If you look at the other quad-core solutions that are out there, or dual-core, what you'll see is they have a single clock and a single voltage. And the issue here is that you can individually collapse these, so if you're not using the CPU, you can turn these off. But if you have a CPU on, it's going to be restricted to whatever the load is of whatever the highest load. So here you can see, if you use intelligent load balancing, in this case, you've divided up your load, so it's multi-threaded, and each CPU is loaded appropriately. So we've scaled down the frequency and voltage to the required load. Whereas the competing device, the same load, all the CPUs will be running at the same frequency and voltage over here on this side. And what you'll find is this is typically how loads look like. Even with something that you think is relatively symmetrically balanced, usually the load's going to be slightly different because there are different points in the application at different times. If you're actually running different applications, they're obviously going to have different loads. And the other thing is when you multi-thread applications, generally not all threads are created equal. So I've seen demos where people are showing web browsing and they show all the cores wiggling. Well, that's not necessarily a good thing because maybe it's just some little tiny thread not doing anything. Well, they've got the other CPU pegged all the way to the max running power. And really, there's only this much work being done in that thread. So just because something's multi-threaded or the core is moving, doesn't necessarily mean you want this core all the way up. So here we have a dual core example. And this was on the 8960. And this is with our ASMP enabled, or on this side it's enabled. And what we did is we set up a script to go through a series of web pages, and here you can see the activity of the CPU. We have it on this side. And we have iHeartRadio running in the background, so it's streaming music, and it's loading web pages. And you can see, without doing anything explicit, we have this technology running in the background, and it can scale down the frequency and voltage to what's needed to run these applications. And so it can scale down the power appropriately. In this case, it's about 33%. Some of you may be curious about what's going on here. So both cores running in lockstep. And the power seems to be higher for the browsing than the audio. That's because they're different applications. So even if the CPUs may be running at the same frequency and same voltage, the power